Hello, my name is Christopher Nelson, and this is my MEMS 5001 optimization final report video on the optimization of a piston. There are many different internal parts that work together in an internal engine. For this project, let's focus on the piston. The piston is a moving component that is contained within a cylinder wall and is made gas-tight by metal rings that encircle the piston. There are many different designs of pistons that have been utilized within internal engines since the very beginning, the purpose solely being to maximize its efficiency. Some of the changes include the type of metals used in manufacturing, the design of the top of the piston surface, along with design changes in the skirting, and the pin that connects the piston to the connecting rod. This process is otherwise known as optimization. In the world of engineering, there is lots of information that goes into the design and reasoning of why pistons are shaped and formed as they are. Most of the research done is on the materials used in pistons to ensure they can sufficiently run under the forces applied during engine runtime. Forged pistons are the strongest and the most economically developed pistons. They are made from forged steel that disperses heat more evenly across the piston, allowing for higher operating temperatures with longer durability even at higher amounts of force and pressure. The model shown was developed in SolidWorks as a representation of a typical four-cylinder engine. A piston in an engine will have to constantly endure combustion and pressure forces that are being applied to the surface of the piston. A Porsche 911 turbo car was used as a model in determining typical forces applied. Before calculations of said forces could happen, some assumptions had to be made. It was assumed all four pistons undergo the same conditions in the model, therefore only the one piston simulation had to be done. As in the moving motion of the engine, one can see all components other than the lower block moving in unison. This was used in determining the most optimal solution. A static study was conducted on a piston to simulate stress to determine the von Mises stress, displacement, and strain that the piston undergoes with the two mentioned forces applied to the piston's top. Unfortunately, due to technical difficulties, the optimization studies could not be performed properly. However, the software managed to save approximately 15% of computational data that can be seen in the results section after approximately 2 hours of computing before timing out. As stated previously, here is the example of my assembly, and as you can see, the model is working just as a typical four-cylinder engine would work. I made sure to keep the most generic shapes of the pistons. This was so that when optimizing the piston, I can obtain the optimal and most efficient design of the piston head. The images in the slide are color mapping diagrams outputted by SolidWorks from 2 study runs, the static and failed optimization results. The SolidWorks optimization functions try to run multiple simulations, and when done will choose the most optimal solution. For this reasoning, I was only given the iteration that the test was on at the time of the software failure. Through prior knowledge and a little bit of research, the pieces in which the software outputted are not ideal, as the pieces that SolidWorks says can be removed would potentially allow for blow-by within the piston chamber, as well as there would be a lack of separation between the piston rings. With just a little bit more computing power or a potential other software, then the final iteration of the piston optimization could be performed. With the opportunity for more research and testing capabilities, a new design that probably hasn't been developed yet could ignite a spark in a new and innovative design for the piston that could change the research and development for communities such as JE Pistons, CP Carrillo, and Mali, where these engineers try to develop new ways to design and create a piston that is 100% efficient and can handle any type of loads and forces applied to it. These forces include heat, combustion force, and pressure within the cylinder chamber. This will result in a piston design that works in all vehicle applications, from daily driving to racing applications. Thank you for your time.